through a rather dynamic phase of its lifetime. Stand by. The comet has just gone through one of the most dynamic phases of its lifetime. It's just passed in its closest point to the sun. We call it perihelion on December 28th. And at that time received a maximum amount of heating from the sun it would ever see. And also the tail was forced to swing from one orientation around to another as the particles from the wind, particles from the sun, which we call a solar wind, pushed it around so it was always trying to face outward from the sun. Now it was moving along at a pretty good clip at this time. It was moving at about a quarter of 1 million miles an hour. At that rate, it would be able to get to the moon from the Earth in about 1 hour, rather than the customary 3 days it's taken us in the lunar program. And it was relatively close to the sun. It was about a little over 13 million miles. Now we have seen a fairly pronounced change during this period of time. And I think we have recorded a fair amount of it in words, in sketches, and certainly with the ATM data. Okay, we'll break here now and go on in and pick up the remainder of the discussion on the ATM instruments. Perhaps one of the most useful experiments and instruments we have on board to learn about Comet Kohoutek is the XUV slit spectrograph, which is a rather long title. What it does is to look at a very small segment of the comet and determine what is various colors of light emitted in the extreme ultraviolet range. Of course, again, these are colors which you and I cannot see, but which the instrument can. Now, what's so particularly good about this instrument is that it's able to resolve the colors to a very fine detail. We call it spectral resolution. It's able to pick out one wavelength from another very accurately. This allows us to look at the signatures of light put out by the atoms, each atom putting out its own particular signature at a given wavelength. And we can do that now quite accurately and thereby get a better understanding of what the comet's composition is. The XUV slit instrument is controlled from this portion of the panel. And another word perhaps, it's unlike the previous instruments we've talked about, it doesn't take a picture of the sun. It only looks at a very narrow slit, something perhaps resembling the geometry of that pencil. It's about 1 arc minute long, which is a 60th of a degree in terms of what it sees, and very much narrower than that dimension across. That's about 1/30th of its length. So it sees a very small element of space. That's been most useful to us on the sun, and we hope it will in resolving features on the comet. We have another instrument on board which does something of a similar nature. We call it the scanning polychrometer spectroheliometer. Now, all those big words put together go together with this instrument, and let me try to explain it. It's a bit like the TV that we're using right now. The TV takes a look at a picture, one little small element, and traces across, then moves down another row and traces across, and in that way builds up a picture. Well, this instrument does the same thing, and it's able to do it at the extreme ultraviolet wavelength and ultraviolet, mostly in the ultraviolet. But it's also able to do something else. It's also able to choose the frequency or the wavelength at which it will make those observations. It's also able to sit still in a very small element of space and scan across all of the wavelengths that it has at its disposal. So in that way we can perform two functions. It has 6 different detectors all working at the same time, so you can build up either 6 pictures at the same time or learn a little bit more about the spectrum with several detectors. Like a TV camera, it does not record its information on film, but records it in the way of electronic data, which can be sent down to the ground rapidly. And in that way, we can analyze in one day and change observing procedures the following day. That's been most useful to us, observing the sun, and we'd hoped it would be in observing the comet. So far what it's told us is that the strongest emission we see from the comet is from a hydrogen line, we call it hydrogen Lyman alpha, a very primary emission from hydrogen. We expected to see that. We have not seen a great deal many other lines of strong emission. However, we do realize that this instrument was built for observing the sun, which is many, many times stronger in intensity than the comet. 2 other instruments we have on board, which we've used to study the sun and learn quite a bit about, and which we've turned now onto Comet Kohoutek, are the X-ray instruments. The X-ray telegraph, or excuse me, the X-ray telescope on this portion of the panel, and the X-ray spectroheliograph, another big word, meaning that this also gets a little bit of information about the wavelengths in X-rays, as well as just a picture of the sun in X-rays, and in this case, trying for it to learn something about the comet in X-rays. Now, we don't expect much emission, if at all, in the way of X-rays from the comet. It's far too cold for that. But there is an outside chance that if we have a major flare from the sun, that the X-rays from this flare will cause the comet to fluoresce. By that we mean that the high energy emissions from the sun will stimulate the gas around the comet, and in that way cause it to emit radiation of a little bit lower intensity, and which is also in the X-rays, and tell us something about its composition. Now, another thing we can learn from X-rays is absorption. Absorption of X-rays from stars behind the comet. Hopefully, there have been some X-ray sources behind the comet, and during very long time exposures, we will be able to observe what the stars look like as the comet's tail is in front of it, and then at later times observe what the stars are like when the comet is not in front of it, and in that way learn a little bit about the composition of the material in between. That is, the composition of the material in the tail which has absorbed the X-rays. All in all, the ATM has proved to be a very versatile set of observing instruments. We found that just because they were built with extreme capabilities, one able to resolve very faint light, the white light coronagraph, one able to resolve extremely fine detail in terms of color or wavelength, the XUV slit spectrograph, and the XUV spectrograph spectrograph, giving us a very good picture of the comet in ultraviolet, and perhaps the X-ray instrument and the scan spectrometer, as we call it for short. All of these instruments combined together, although originally intended for studying the sun, have given us, we feel, an excellent tool for learning about the comet. Now we'll go on down into the lower portion of the space station and look at what we have in the way of observing instruments out of the scientific airlock. Okay, we're now down here in the forward area of the orbital workshop, and I'd like to show you some of the equipment and describe a little bit about how it works. Now, the main part of it all is the articulated mirror system. What we essentially have right here on my right-hand side is a hole in the wall, if you will, and a way of putting instruments up against that hole in the wall, which we have a door for on the outside. We put instruments up against that hole, and we're able to take observations of the outside. The door stand by. Why don't you just check that? I got asked a question. I got off my train of thought. Okay, I'll pick this up and try it again. We're down here in the forward area of the orbital workshop, and I'd like to show you a little bit of the equipment that we're planning on using and have used for observing the comet out of the scientific airlock. Now, airlock is, for us, is just a term for a hole which is cut in the wall and which we can put instruments up against and use that hole to allow the instruments accessed outside for observations. Now, the heart of almost all of the observations I'll discuss right now is the articulated mirror system. Without it, we'd be at a loss to really make a large number of the observations we have been able to do. Essentially what it is a way which we can take observations of almost any point over a hemisphere of the sky or this whole area which we can look out here without moving the spacecraft around. We do that with a mirror system which is inside. It's projected out, and then this being the mirror, it's able to reflect light back in. For example, if we wanted to reflect light back in from here to there, we put the mirror at this angle. We're able to rotate it all around like so, and we're able to rotate it in this direction also. In this way, we're able to make observations here and still have the spacecraft and what we call a solar monocular still pointing at the sun, which we need for electrical power and for the solar observations. The first instrument, which I think is an excellent instrument for the types of observations we've been making, is the far ultraviolet electronographic camera. And that's this instrument here. The real attribute of this is that it can take pictures of what emissions are in the ultraviolet at extremely faint intensities. It's about 20 times more intense or 20 times more sensitive than the normal camera. It uses a high energy source, high voltage at least, 20,000 volts. And when looking out of the scientific airlock, it's got about 9 degrees of field of view that I can see. And we've taken it out on the last EVA. Matter of fact, on the last two and made some good observations with it EVA, where it can see a much larger part of the sky. We have a way of aligning what we want to look at, if you will, and that's been most useful also in conjunction with the mirror system and understanding a little bit about the comet in ultraviolet, as well as in the optical or in the visible range. So all told, we have quite a full complement of observing capabilities on board Skylab. And when we get back, I'm sure there's going to be lots of people, including ourselves, interested in look at the data and learn an awful lot more about Comet Kohoutek. Thank you. Bill, would you cut the VTR, please? Okay, here you're able to see a close-up of the far UV electronographic camera. The sights, which we've used for aiming. And one thing I ought to mention about this is the first time this was used in the space program was on Apollo 16. It was taken to the moon and directed back to Earth. Learn a little bit more about the oxygen and hydrogen, which is in the upper atmosphere of the Earth. Here's a close-up of the UV stellar astronomy experiment. And like most of these experiments, I'm sure they appear to be just boxes to you. All of the action, of course, is on the inside. To us, they appear like boxes too, but when we make the observations, there are certain things we have to do in order to achieve the best quality data possible. Some require a fair amount of judgment, some technical skill, but it all involves knowing fairly intimately what's inside of these boxes. Observations, which I'd like to show you how we do, are fairly straightforward and kind of fun. We use a mounted camera. We've been able to use it for about the past month or so. And we use it out just one of the windows here in the multiple docking adapter or in the command module. We've been able to monitor, watch the change in the brightness and in the form of the comet as it's moved in towards the sun. And we've been able to photograph it with some fairly long time exposures with very sensitive film. I think this will give us a very good history of what the comet has looked like since we arrived here a little over a month ago. Now another way to observe it, and we don't bring any data back on this other than what we've put in voice and able to draw, sketch, is the use of binoculars. And this is just a very enjoyable way to do it. I'm sure that some of you, once it becomes visible to you at night, will be looking at it the same way, just after sunset, the same way we are now. We get 15 sunsets a day, however. It's really an impressive and enjoyable sight. Very awe-inspiring. I think what it does is just make you very appreciative of good old Mother Nature. It's something I know you'll all enjoy, and it ought to be coming up soon.